Good morning. How are you? I hope you slept well. So, welcome to another lecture on arithmetic for computers. So, today we will finish this second part of the module arithmetic for computers. And as always, remember that part of the material shown in this slide is taken from the book. So yesterday we reviewed the floating point standard IEEE 754, and today we are going to see how we do additions, multiplications, how those additions and multiplications are translated to hardware, and we will see also equivalent instructions in assembly language. We will finish showing what is a subword parallelism. Okay, so let's start then. So, first of all, we are going to consider the addition in floating point, and we are going to imagine that we only have four-digit precision. So imagine now that we have two decimal numbers, in this case 9.999 multiplied by 10 power 1, and we want to add this number to this other decimal number, which is 1.610 multiplied by 10 power minus 1. Okay, so we want to perform the addition of those two floating point decimal numbers. So we are going to use the following method, and I'm using this method because it will be the method that we will afterwards implement in hardware. So first of all, this method says that we need to align the decimal points. What that means? That we need to make sure that the exponent here in this case and here are the same. Okay, so this method says that we shift the number with a smaller exponent. In this case, the smaller exponent is minus 1. So what we do is we shift this number to the right and increase accordingly the exponent. So in this case, we have moved this number, to the left. We have shift this number in two positions, and we increment the minus 1. One position will be 0, and the second position will be 1. Okay, so this is the first thing we do. We shift the number with a smaller exponent in order to make it match the larger exponent. So now that we have the two exponents are the same, we add the significance. So in this case, as this is an addition, we are going to add 9.999 plus 0.016. Notice here that in the previous step we lost precision. We lost this one, and we lost it because we only have 4 digits. Okay, so we are losing precision. And then we here just add this number to this one, and we have the resulting number. The exponent is the same as before. Okay. The third step will be normalizing the result. So remember that for us, normalizing means that we only want 1 digit before the point. So in this case, we have 2 digits before the point, and we want only 1. So what we do? We shift the number, we shift the point to the left and increase the exponent accordingly. Okay. In this case, we have shift it 1 position, so we increase this 1 position. If we were shifting the point in the other direction, instead of increasing the exponent, we will decreasing it. Finally, we need to round. Why we need to round? Because here we have 1, 2, 3, 4, 5 digits, but as we have mentioned, we only have a precision of 4 digits in this example. So we need to round this number. Remember that if the last number is 5 or greater, we round the previous number up, and if not, we just remove that. So in this case, for rounding up 15, we round it up to 2. Okay, so with this, we will have the number round. sometimes when we round the number, we need to renormalize it again. So if that happens, we just need to go to step 3 again. Okay, so how those steps are actually represented in how this method is actually represented in a flowchart for the algorithm. So this is similar to what we saw before, for showing to what we saw yesterday in previous lectures for other algorithms. In this case, this is what we have just done, but now in a more formal way. So we start. The first thing we have done is comparing the exponents and make the smaller one match the greater one. In this case, it's taking into it's saying exactly that we compare the exponent of the two numbers we are going to add and adapt the smaller one until it matches the larger one. Okay. Then what we have done in step 2 is adding the significance, and afterwards we have normalized the result. Remember, normalize means we only want one digit before the point. And the fourth step is checking, okay, do we have overflow, underflow? We will see later what this means. If this happens, we will just throw an exception. And if everything is okay, we will round the significant to the appropriate number of bits. If after rounding it, it is still normalized, then we finish and we are done. And if it is not normalized, we jump again to step 3 in order to normalize it again, check the overflow, round it, and check again if it's normalized. Okay, so this is just what we have seen in the previous example, but in a formal way. So now we are going to see how this algorithm is actually converted into hardware. Remember that we have seen in previous lectures an algorithm for binary multiplication, an algorithm for binary addition and division, and we have seen the hardware associated. So now we are going to see the hardware. This hardware is much more complicated, so I'm just showing it you for reference. So it's not I will not ask any question regarding this hardware in the test. It is just for reference, and as I have mentioned, and yeah, it's something we will leave left for the future, for module for stage 2 or 3. Okay, so as I have mentioned, it's a bit more complicated, but initially we have here the first number we want to add in floating point following the standard IEEE 754, and here we have the second number, and at the end we have the resulting number. Okay, so what we are actually doing here is what we have mentioned in the previous algorithm. So the first step is comparing the exponent and make the smaller exponent match the greater one. Then the second step is adding the significance. See that we have here an arithmetic logic unit. Remember that we have seen this hardware element, and arithmetic logic units are used to do add operations, and, or, and so on. Okay. Then the next step is normalize the number. We have here what we have done in the method is shifting the number left or right and incrementing or decrementing the exponent accordingly. And the fourth step is rounding it. We just assume that there is a box here that rounds this element. We are not interested in how this is done right now. And if necessary, we need to look back if at this point the number, if we need to renormalize it. And if not, we are not, and we will have the number, resulting number at this point. Okay. As mentioned, this hardware is just shown for reference. I don't plan to ask anything related to this hardware in the test. Okay then. So now I have an exercise for you. So we have done the previous example using a 4-digit decimal number. So now we are using 4-digit binary numbers. So we have 1.00 and minus 1.110. The equivalent values in decimal are those ones. You can use this in order to check the result. So what I'm asking you now is, following the four steps we have just seen now, and I have placed this in this slide for you. So can you tell me what is the resulting binary number with 4 digits using the algorithm we have shown? Okay, I'm going to give you 3 minutes, and I'm going to add a link in the Q&A in order to a form to answer this question. Okay, so yeah, good luck. Okay, thank you. The time is over. Let me check if some of you. Okay, we have very few responses. I will wait a bit more to see if some more responses arrive. Okay, I only got 7 responses. Okay, so I'm going to show you how this is actually done. So first of all, yeah, some people is telling that the method is still not very clear. So hopefully after this explanation is going to be clear. Someone is also making a good question. Someone is asking why when we compare the two numbers, we shift the smaller number instead of the larger number. So imagine if we have a number with a larger exponent, it means that it contains more important information than the one with a smaller exponent. So imagine that if we only have 2 digits, we prefer to maintain the most significant digit than the less significant one, because the most significant digit contains more important information. So if I have only 2 digits to represent 100, I would like to represent it with 99. And it doesn't matter if I lost 99.1 or 0.9, okay? So this is the reason for maintaining the most significant part, because it has more important information. Okay, if it's not clear yet, let me know. So let's come back to the example. So we have this 4-digit binary example. So what we are doing here is following the same steps as before. First of all, we align the exponents. In this case, the -2 is the smaller one, so we shift the number and we increment or decrement the exponent adequately. Okay, so in this case, we have shift the smaller exponent to the right, and we have incremented, we have shifted to the right 1 position, and we have incremented the exponent 1 position. So now the exponents are the same. So the second step is adding the significance. So in this case, 1 plus 0.11 point, we have this result here. Okay, remember that we are in binary, not in decimal. Okay, after doing this, we normalize the result. What do we mean by normalizing the result? That we want only 1 digit before the point, and as we are in binary, we want that digit being 1. So here we need to shift 1 position, 2 positions, 3 positions to the left. So if we shift 3 positions to the left, we decrement the exponent 3 positions. So it was 1 minus 3 position. It was -1, sorry. We subtract 3 positions. We decrease it 3 positions is -4, and we have it normalized. And there is no underflow or overflow. We will see what overflow and underflow means later. And then we round it. In this case, we don't need to do anything. The number already has 4 digits, and we don't need to change it. In order to check the result, as we have here the decimal equivalent, we can do the operation and we can check that this is the equivalent. Okay? Hopefully it's more clear now. So let's try to do now the same, a similar thing, but instead of adding floating points values, we are going to multiply them. The process is very similar. So we are going to start with an example. In this example, as before, we are going to consider decimal digits, and with only 4 digits. So first of all, we need to, in this case, add the exponents. So in a multiplication, we add the exponents. In this case, we do 10 plus -5, which is 5. So the new exponent for the multiplication of those two values will be 5. Then we multiply the significance. In this case, the significance, remember, are 1.11 and 9.2. So we multiply them, and remember now we are in decimal, so this is a regular multiplication, and we get the value. And this value, we add the sign, the exponent we have calculated previously. So now we have the result of this multiplication. So the problem is that here, now we want to normalize it. So we want only 1 digit before the point. So in this case, we are shifting the number to the right. So we are incrementing the exponent from 5 to 6 because we have shift the number to the right 1 position. Okay. With this, we have the number normalized. Problem is now that we only have 4 digits for representing it, and here we have 1, 2, 3, 4, 5. So we need to round the last one. In this case, if we round the last one as it's less than 5, we just can remove it, and we will have the number rounded and normalized. So with this, if it were necessary to renormalize it again, we will just go to step 3. In this case, it's okay. So now we are going to determine the sign. In a multiplication, this method says that if the signs, in this case, if the signs of the exponent of the digits we are going to multiply have the same sign, we the sign is positive. So if I'm multiplying 2 positive numbers, the sign is going to be positive. If I'm multiplying 2 negative numbers, the sign is going to be positive. And only if the signs differ, I'm going to have here a negative sign. Okay, makes sense? So this sign will only be negative if the signs of the values are different. Otherwise, it will be positive. So let's see this in a more formal way. So this is the same 4 steps we have, the same 5 steps we have just done in the previous example, but in a more formal way. So first of all, we start, and we, as we have mentioned, we subtract the exponents. In this case, remember that in floating point standard that we have seen, the IEEE 754, we have mentioned that we are using bias exponents. So in this case, what the method says, okay, for the binary, we add the bias exponents to the 2 numbers and then subtract the bias from the sum to get the new bias exponent. Okay, we will see an example later. Remember that for single precision, the bias for the exponent was 127, and for double precision, it was 1023. So then we will go to the second step, which is multiply the significance. After that, we will normalize the product, shifting it right and incrementing the exponent. If there is overflow and underflow, as I have mentioned, we are going to see later what this means. We just throw an exception. If not, we continue. So we continue to step 4, which is actually round the significant to the appropriate number of bits. In the previous example, we were using only 4 digits. So the result of the operation had 5 digits, so we rounded it up to 4 digits. And then what we have done is check, okay, is the number still of normalized? If not, we need to go to step 3 here, and then normalize it again, check overflow, underflow, round the significant value, and doing this loop until it's normalized. And once it's normalized, we set the signs of the product. As I have mentioned, the signs of the product will be positive if the sign of the original operands are the same. If both signs are positive or if both signs are negative, then the sign of the product will be positive. If the signs of the operands or the original operands are different, then the sign will be negative. Okay, and with that, we are done. So I'm not going to show the hardware here. The hardware here for multiplication is very similar to what we have seen for addition. Instead of having doing the addition in the arithmetic logic unit, we are multiplying the significance, but the rest is similar. This floating point arithmetic hardware usually, apart from addition and multiplication, it usually do other operations such as subtraction and division. It also performs operations like conversion from integer to floating point. And one interesting thing that will make a lot of sense in module 2 is that those operations, those steps that we have seen, can usually be pipeline. This is something related to microarchitecture, and is something you will see in module 3, in stage 3 and 4. Okay, so now we are going to do another exercise, but this case multiplication, similar to what we have done with the addition. So we have the same values, the same operands in binary, but in this case, we are going to multiply it instead of adding those numbers. So we have here again the method that I have just shown you with the 5 steps, and I'm going to give you again some time to do this, and I'm going to place also a link to a form in the Q&A. Okay, so good luck. Okay, the time is over. Let me check if this time more people has finished. I don't see any response. That means probably it was too complicated, or that you want more time. Okay, I don't see any responses, so maybe it's better that I show you how to do this.
Hello, Carlos. I think they're just having trouble posting on the form isn't working. So a lot of students are just saying that it's not working. That's okay.
Okay, thank you, Andrew. Okay, so doesn't matter. We are going to continue. I'm going to show you the solution, and with this you can check if you did it right or not. Okay, so let's see then. in order to multiply those two numbers. So we are going to follow the method we have just seen. So the first thing is to add the exponents. So before, when we were using the decimal, we have just added the exponents. But I have mentioned you that in floating point, in the Stardank we are using biased exponents. So when we use the unbiased exponent, adding the exponent is an addition, a regular addition. But if we are using the biased exponent, we need to add the bias. In this case, in single precision, the bias is 127. Okay, and we just add 27 to the first exponent, 27 to the second exponent. We then perform the complete addition, and we add again, we subtract the bias again. Okay, and we add again the bias. So we need to do it this way, okay, in order to get the real exponent. Okay, we need to add the bias to the individually to the exponent, then subtract the bias, and then add it again, okay, to get the bias exponent. Then once we have the exponent, in this case we are going to use the unbiased one for simplicity, but I just wanted to show you how this will be done with the bias if we want later to represent it in using the standard format. So now we multiply the significance. Remember, this is a binary multiplication. We multiply 1.00 by 1.110. Okay, and then we normalize the result and check if there is overflow or underflow. As I have mentioned, we will explain. We will talk about overflow and underflow later. So here we have the exponent, and we see we have it already normalized because we have 4 digits and we don't need to do anything here. Now we don't need also to round anything because everything is fine. The number has 4 digits, so everything is okay. And now we determine the sign. So in this case, the first operand had a positive sign, but the second one has a negative sign. So the sign of the operands differs, so the sign of the multiplication is negative. And we can check this result with the decimal values in order to see that it's everything is correct. Okay. So now let's see to what is this that we have mentioned, overflow and underflow. So we have already seen overflow in integers, but now we are going to see what is overflow and also underflow in floating point. So overflow, similarly to integers, is what we have a value too large for representation. Okay, this is similar to what we have already seen. Underflow, and this is new, is when the value is too small for the precision we have. For instance, with single precision, we are limited to we are limited in the precision we can indicate for a number. Or in the example before, we only have 4 digits. So we need, if the result of a multiplication had 5 digits, we needed to round it up. So with this, we are lost in precision, and this is what we call underflow. Okay, when the value is too small for representing it. So graphically, so imagine we have for the range of single precision numbers. So we have this maximum value. Remember, the 23 is the number of bits of the significant, and the 127 is the numbers of position I can represent with the 8 bits of the exponent. And then the lowest, the smallest value I can represent is the same, but doing it negative. Okay, so this will be for single precision. For double precision, it's the same, but what we are changing here are, in this case, we have 52 bits for the significant, for the fraction, and then we have we can represent with 11 bits in the exponent. We can represent up to 1023 positions. So this will be the range then for double precision numbers, and the range for single precision numbers. This will be the maximum number I can represent, and this will be the minimum number. So any number larger than those values is what we call overflow or positive overflow. And any number smaller than those values is what we call negative overflow. Okay? So this is graphically, in order to get those maximum numbers and minimum numbers, we just do this operation, and is the thing is what I have just explained with in the previous slide. Okay, we were using here the number 23 because it's the number of bits that we can represent in the IEEE format, in the IEEE 754 format for the fraction. And for the exponent, remember I have 8 bits, which means I was able to represent 127 positions. Okay, and similarly, we can do the same for the double precision. We have, in this case, 52 bits for the fraction, and therefore for the exponent, I have 11 bits. Okay, so now let's see what is this. The previous was for overflow, that I think is clear, but now we are going to see something new, which is underflow. So we have mentioned that the range for the single precision numbers was this one and this one, okay? The larger number and the smaller one. And we have mentioned that for the double precision numbers, we have similarly this larger number, and this will be the largest number, and this will be the smallest one. Okay, but here in between is where underflow happens. Okay, so for instance, I'm going to explain later from where we have this 149, but in this case, and I will also do the same later for this number, but for the time being, just believe that we have this is the smaller positive number I can represent. Okay, the smallest one. This is the greater one, the largest one, and this is the smallest one I can represent. So this is, if I want to represent a smaller bit than this, a smaller number than this, I cannot do this. So this is what it's called positive underflow. I'm losing precision. Similarly, if I want to represent a greater negative number than the one indicated by this number for single precision and this number for double precision, it's called negative underflow. Okay, so it means I'm losing precision. I cannot represent a smaller positive number than this value for single precision, or a greater negative number value for this than this number here. Okay, and this is what we call underflow, the loss of precision. So these numbers here, 149 and 1074, are calculated in the following way. For single precision, so we just do this operation here. So we have the 23 bits of the fraction. In the case of the single precision, the 127 elements I can represent with the 8 bits of the exponent, and by doing this operation, I have this number. Okay. Similarly, I can do the same operation for double precision, and with this, you get the values for getting the underflow ranges. Make sense? Okay then, so what instructions do we have in LEGVI for doing this addition and multiplication using floating point? So in LEGVI we have separate floating point registers. So remember that until now we have seen registers that we use for integer operations, and right now what we have is 32 single precision registers from S0 to S31. Remember that till now we have 32 registers that we'll call starting with an X, and these ones are with for single precision start with S, and for double precision start with D. Actually what is happening is that the single precision one is stored in the lower part of the double precision register. Okay, so actually we only have 32 double precision registers, but we also can use the the S0 register to refer to the lower part of the double precision 64-bit register. Okay. So the floating point instructions, that we are going to see for LEGVI, operate only in floating point registers. Okay. So, and the instructions, for instance, for loading and storing instructions, instead of using the instruction we have seen until now, we can add an S or a D. Respectively, we want to load a single precision value in a single precision register, or a double precision value in a double precision register. Okay. So for adding and subtracting and multiplying, again we have the F indicating that it's a floating point instruction, and we have the S for single precision and the D for double precision. Okay, I'm just showing these instructions for reference. You will not be asked these instructions in the class test. Okay, and for comparing and doing branch operations, we also have operations for single and double precision. Okay. So now I'm going to show you. So imagine that we have this code which in C just converts from Fahrenheit to Celsius. So I'm going to show you how this will be converted into LEGVI code. Okay. So we have the C code here. I think it's clear. Float, remember in C, float, it will be equivalent to single precision, and double would be equivalent to double precision. So here, as this function is using floats, we are using single precision. Okay. So then we have a procedure in LEGVI. We are going to call it Fahrenheit to Celsius, the same way as the C function. What we do is we load from memory a single precision value, which is placed at the base address indicated in this register, and with this offset, or the offset indicated in this constant. Okay, in this case we are making this. We are saying, okay, register S16 will be equal to 5.0 in the previous example. Okay, so this number was in memory, and I have loaded it into this single precision register. It's the same that we have done before with regular registers, but now we are using a single precision register, and that's why we have an S here in the load method. So now we load the 9.0 flow, the 9.0 value. We are going to load this in another register, in this case S18, and in this case we are going to assume that this value is placed at the same base address in x27 plus this offset. Okay. Now I'm going to perform the division, 5.0 divided by 9.0. So, and I'm going to store the result in S16. So in this case, I'm using the floating point division single precision, and I'm using single precision registers. Okay, then I'm going to load in S18. I'm going to reduce the register because I don't need it anymore. I'm going to load here this value, the 32.0, which I'm going to assume that is in this offset in memory. Once I have it, I'm going to do this subtraction here. Okay, I'm going to subtract this. I'm assuming that this input argument is located in register S12. Okay, so I subtract this. It's a floating point subtraction, single precision, and I do the operation. And finally, I do the multiplication, which is again a floating point operation using single precision registers. And I return to the colleague. Okay. As mentioned, I'm just showing this for you for reference. We will only be using integer values in the class exam. We are not going to use floating points in LECV8, okay? Now, let's move on to subword parallelism. So what is subword parallelism? It's a very simple concept. So it's the idea that applications can perform the operations in parallel, and with this we can improve the performance. For instance, if I have an arithmetic logic unit that can add at the same time 128 bits, so it can perform 16 8-bit adds in parallel instead of just adding 128 to 128. I'm going to show you a graphical example later. The same will happen for instead of having 16 8-bit adds, I could do 8 16-bit adds with this 128-bit adder, and a more simple way will be doing 4 32-bit adds in parallel. Okay, this is called single instruction multiple data, because in a single instruction I'm going to add multiple data which is located in the same register, in the same operand, input operand of the instruction. In RB8, and notice here that I'm saying RB8, not LECV8. In LECV8 we don't have this. In RB8 we have 32 128-bit registers, which are called V0 until V31, okay? And they work with integer and floating point precision. So for instance, remember that before I have mentioned that instead of doing adding 120 bits to another 120 bits, I could do adds in parallel. So I could do 16 8-bit adds in parallel. And for doing this in RB8, I will have this notation. So instead of just indicating the register, I indicate the register point 16, and the B is for integer. Okay, and with this I will be doing 16 8-bit operations, or 16 8-bit adds instead of doing one add of the whole register. The same happens with floating points. In this case, I use the floating point addition, and instead of the B, I add here S because I'm using single precision. And this will do the same, okay? But with 4 32-bit adds. I'm going to show you this graphically. So what we are saying here is, if I have an input register of 128 bits, let's say we have a value A in the 32 bit in the leftmost quadrant, then we have B in the third quadrant, C in the second quadrant, and D in the first quadrant. So all this register has 128 bits, but we can split it in 4 quadrants of 32 bits. If I have a similar register to split it in the same way, and I want to perform, instead of adding 128 bits to 128 bits, what I want is 4 32 bits addition in parallel. So I can do that with using the notation I have shown you previously. And the result will be that in this quadrant here, I will have A plus E. In this quadrant here, B plus F. In this quadrant here, C plus E. And in this quadrant here, D plus H. And the important thing is that all these 4 adds will happen in parallel. So with only one instruction, with only one addition instruction, we will be doing 4 additions in parallel. Okay, this is what we call subword parallelism, or simple instruction multiple data. With only one instruction, I perform an addition in multiple data. Okay, so today we have progressed in the floating point knowledge. We have seen how is addition and multiplication actually done in LECV8. We have also seen what is overflow and underflow and the equivalent instructions in LECV8, and we have also mentioned what is subword parallelism. In the next lecture, we will start the third part and the last part of this module, which is the basic logic design. So we started in the first part with assembly code. We have seen in the second part how some of those instructions, arithmetic instructions in the assembly code, are actually performing hardware, and now we are going to go down to the basics and to see how this is implemented with circuits. Okay. Let me check if I have time for a quick question. So so someone is asking, what does the V mean again in the subword parallelism instructions? Let me check. Yeah, so in this case, the V means that, as is mentioned here, I'm saying that in RB8 you have 32 120-bit registers, which are referred by this V. So from V0 to V31, we have 32 registers of 120-bit bits. So in this case, V1 refers to register 1 with 128 registers. Okay, so we don't have time for more questions. So remember that we have the ticketing system for your questions, and we are always happy to answer your questions there. Today we will have a lab. It will be published at 1. It will be the last lab for the part 2 of the model of the module. It will be still on the topic of instructions of the computer. Okay, thank you so much for listening. I hope you enjoy it, and see you next week. Have a nice the rest of the week, and bye bye. See you.